Now that we talked about the complex number system, let's go back to polynomial functions and see what it means there as far as zeros go. So polynomial functions can have real zeros, imaginary zeros, or a mixture of both. A complex number can be a zero of a polynomial. So let's look at this example, and it's in factored form as the equation, and the graph is shown on the right. We have f of x equals the product of x plus 2, x minus the square root of 3, and x squared plus 1. So remember, the zero product property says either x plus 2 equals 0, if we were to find the zeros here, so x would be negative 2, or x minus the square root of 3 could equal 0 if we were trying to find the zeros. Remember, we would just set that equal to 0 and solve this equation with the zero product property. So the second factor, if we had x equal the positive square root of 3, that would cause that to be 0. And then we have a little bit of algebra to do here. We need to subtract 1 from both sides, and then we have x squared equals negative 1. And then we have the square root property of where we take the square root of both sides. We'll have both the positive and negative square root of negative 1. Well, we just defined what the square root of negative 1 is, and that is I. So x could be plus or minus I. So the two real solutions are where the polynomial crosses the x-axis, and we have negative 2, and its coordinates, remember, would be negative 2, 0. We also have the irrational real root of the square root of 3. So we have the square root of 3, 0 are the coordinates. And then these other two zeros are imaginary zeros, and they happen somewhere else on the curve. They are not zeros that are real. If they were, they would be where we cross the x-axis. So getting a little ahead of ourselves, we have 4 complex zeros here. So we know that real zeros correspond to the x-intercepts, but imaginary zeros have no graphical significance. In other words, we don't see them. We don't see imaginary zeros on a graph.